Hello everyone, in this video I'm going to talk about the variance decomposition and measures of it. So actually I wanted to talk about measures of it, but in order to be able to talk about this part I need to first give you an introduction of variance decomposition. So as we know, in a multi-regression model we have yi as, for example, a dependent variable as a function of beta naught, the intercept, plus partial slope for the first regressor plus the second partial slope for the second regressor, and we can keep going until we get the last regressor k x ki plus the error term. And we say the sample goes from the first observation all the way to the nth observation, and we have k coefficients, so the x's go to k variables and we have n observations, so we will keep repeating this equation like n times. So this is like a multi-regression model. We can simply write it in an estimated form, and we say it's basically beta hat naught plus beta hat 1 x1i plus beta hat 2 x2i plus beta hat k x ki, and of course, as we said before, we basically want this error term, which is the difference between the actual value of the dependent variable minus the estimated value of the dependent variable, to be as small as possible. In other words, we basically want the sum from I equal 1 to n squared of this error term, which is equal to the sum from I equals 1 to n squared deviation between the observed and the actual value of y. So the main idea is to minimize the sum of the squared deviation, and that's basically the idea of ordinary least squares. Ordinary least squares objective is to estimate the quantity, which are basically the coefficients of the regression, such that we can minimize the distance or the deviation between the estimated value of y and the actual value of y. So we want to minimize this sum as much as possible, and we minimize it based on, so we do like a minimization problem, right, with respect to the coefficients beta hat naught, beta hat 1, all the way up to beta hat k. That's basically the idea behind ordinary least squares. So we can, like, based on this simple introduction, we can actually write our yi as being equal to the estimated value yi plus a certain amount of estimated errors. If we want to take the if we want to subtract the average of y, we can do so from both sides to create what we call variance. So I can take the y bar, I can subtract y bar from both sides. Okay, so this one is a deviation of the actual y from the average value. This is a deviation of the estimated y from the same average value, and this is your error term. We can also sum this from I equal 1 to n of yi minus y bar, and we can square it, and we do the same thing on the other side from I equal 1 to n of yi hat minus y bar squared plus the sum from I equal 1 to n of ui hat square. We call the first part as the total sum square equal to the explained sum squared plus the sum of squared residue. Okay, we call this one as explained because I can explain it by the components of yi hat. So if you open yi hat, you get what we have here, right? Yi hat is explained because I can estimate these parameters. I can multiply them times the x's and get a certain value for yi hat. So it is the explanation part. So this part is called the explained sum squared, and we hope to maximize this part as much as possible, or you can say it differently, we hope to minimize this part as much as possible. You can also abbreviate this by saying this is called TSS, total sum squared, is equal to explained sum squared plus the sum of the squared mistakes, the sum of the squared residues. This is called variance decomposition. And why is it called variance decomposition? Because as the first part I can call it simply, this is the sample variance, right? So the first part is simply the sample variance is equal to, or the same, I should say actually, the sample variance of yi is equal to the sample variance of yi hat plus the sample variance of ui hat. So each part represents a certain variance for a certain variable. So again, TSS is equal to ESS plus SSR, sum of the squared residual or sum of the squared mistakes. We are going to use this equality to talk about measures of fit. So what are the measures of fit? So we have certain statistics used in order to check whether our model is good or bad, or explains the variations that we have in the dependent variable, and so on. So the first important measure of fit is called the regression R square. What is the regression R square? The regression R square basically measures this part as a fraction of this part. So it's basically, I should say it's equal to ESS over total sum squared. It's a certain ratio, and it basically, if it is 0.8, so 80% of the variations in the model is explained by the different variables I have used in the model. So of course this is it ranges, it has a certain range from 0 to 1. So the range for this R square goes all the way from 0 all the way up to 1, where 1 is 100% explanation. So if this is equal to this, then I'm getting R square equal to 1, which means that all my regressors, all the x's I have in the model, are able to 100% explain the variations in the dependent variable, or y. We can also explain it this way. If I open up ESS and say ESS is simply TSS minus SSR over TSS, or you can write it 1 minus SSR divided by TSS, and we can see these extreme values. So if I have R squared is equal to 0, then my model cannot explain anything, right? And this happens when basically the explanation ESS is equal to 0. So if ESS is equal to 0, then that means all my model is only explained by the mistakes, the residuals, which is very bad, right? This is a very bad model. Why? Because my x's cannot explain the variations in the dependent variable. This is one of the extreme. The other extreme is that R squared is equal to 1. That means ESS is equal to TSS, or my model is 100% explained by the x's I have. And this is like the other extreme, and this is like extremely good, right? And doesn't happen in real life. This doesn't happen in real life. Okay, we usually get like, if R squared is very good, we usually get it like somehow like 80% or something. It's very hard to get like 100%. So based on these formulas, we basically can say that R square is used to measure the fraction of the variance of y that is explained by x. And it's very important to write that it is a unit, it is a unitless measure, which means like do not expect the number to be in dollars or in miles or something like that. It's just a number that ranges from 0 to 1. Okay, so for example, 0.75, if I have an R squared equals 0.75, then 75% of the variations in the x's are explaining the variations in y. The word explained is very important. It's actually, our main measure is called explanation. Okay. Our next measure is called the standard error of the regression. So this is called the standard error of the regression. And the standard error of the regression is another very important statistic. It basically measures the magnitude of a typical regression residual in the units of y. So in R square I said it's unitless. The R square is unitless because whatever the number I get is just a percentage of explanation. But the SER takes the same units of the y. So if my dependent variable is in dollars, my SER is going to be in dollars. If the dependent variable is in miles, the SER is going to be in miles, and so on, because it's actually based on the variance of this variable and the square root of the variance of this variable adjusted for degrees of freedom. So you can define SER as being a statistic that measures the spread of observations around a regression line. Okay, so we want to see the spread of observations. This is y, this is x, this is the relationship. I want to check the spread of the observations around the regression line. So if I have this picture and if I have another one and the spread is really tight, right, then this one, this is x and this is y. This one has like a wide, range of observations. However, this one, the observations are kind of very tight around the population regression the estimated population regression line. Of course, this one would have a smaller SAR as compared to this one. This one would be better, right? Because I can see that I don't have so many errors. The range is very tight as compared to this range. Okay, so the SER basically is a measure of the spread of the observations around this line, the regression line. We call this one the regression line, or you can call it the estimated population regression line, as most of the textbooks they add the word population. But you have to mention that it's the estimated population, not the actual population, it's the estimated population. How can we measure this spread? It's simply very similar to the idea of the variance, but it's the variance of the error term. So, and when I say standard, then I should say it's the square root of the variance of the error term. So, it's equal to standard error of the regression is basically equal to the square root of the sum from I equal 1 to n. It's exactly like when you compute any variance. You take each observation, but now my observation is the error term, ui hat minus u hat bar, which is the average, square divided by n minus 2. Why 2? If I'm saying, let's say I'm starting with a very simple model, so 2 in case if I have one regressor. So if I have one regressor, then I'm basically estimating yi equal to beta naught plus beta 1 xi, right? And I'm gonna have basically two parameters to estimate, and that's why when we correct for degrees of freedom, we just say minus 2. But if I have multi-regressions, to make this adjustment of degrees of freedom more general, a multi-regression model would have a yi equal to beta naught plus beta 1 x1i all the way up to beta kx ki plus ui. So in a multi-regression model, we would write SER as follows. Basically, it's going to be like the sum from I equal 1 to n of ui hat minus u hat bar divided by n minus k betas minus 1 for the intercept. So this one is counted here, 1 for the intercept, and then you count 1, 2, 3, 4, 5, 6 all the way up to k, and this counts for the k parameters to be estimated. Okay, so those are basically two versions of the SER depending on whether your model is using just one x or more than one x. What is important in either of these is the following, and this is very important. Let me take the simple case by saying SER is equal to the sum 1 over n minus 2, the sum of I equal 1 to n, ui hat minus u hat bar, okay, and then 2 here because suppose I have just 1x single regressor, okay. I just want to show you something very important. So based on the assumption, we have an assumption in OLS based on the OLS assumption, or the first assumption. We said that the expectation of the error term given, let me just correct this letter E, it's too big, so not to be confused. So the expectation of ui given xi is equal to everything about this error term, which is equal to 0. And I said before that you can actually write it this way, the sum of all ui hat over n, which is basically equal to u bar, which is equal to 0. So anytime you see u bar, just substitute it by 0, and we can do so here. Okay, I'm sorry, I missed this square. And we can do, let me check, I have the square in my previous, I missed the square. Okay. All right, so we can always remove this part and substitute it by 0. So that's why the SER is usually written this way: the square root of 1 over n minus 2, the sum of I equal 1 to n of ui hat square, and you forget about the u bar part because it's actually by assumption is equal to 0. Okay, and the last thing I want to write here is the SER has the units of ui, which in turn, sorry, it's very slippery, which in turn has the units of yi. If you don't understand why, like the idea here, if the ui is in cents, then this one is going to be in cents. If this is in miles, then this is in miles. If this is in years, then this is in years, and so on. And the idea is basically ui is made out of the y. So it's basically y minus yi hat squared. So it's actually made out of the y. So that's why whatever the value, or I mean like the unit of measurement of y, it's going to be the same unit of measurement of ui. All right, let me stop here. I'll record another one.